All right, today we're going to continue looking at ways of determining an original function from its rate of change. And, when it comes to rate, a function and its rate of change, to me the most intuitive way to look at it is in terms of distance and velocity, because velocity is the rate of change of distance over time. And so what I want you to do is actually pause the video right now. If we were in class, I would give this activity as a warm-up. To take a look at these, this example 1, these 3 questions in example 1, and try to determine, I guess the first 2 are just looking at the velocity given a displacement or distance graph. And then the last one is to try to do the opposite. You're given the velocity and you need to graph the distance. So I want you to take, so like I said, pause the video and try this and come back and we'll talk about it. All right, so to graph the derivative of this distance function, we just need to look at the slope of this graph at any point. And since it's a nice, in this case, it's just a really made up of straight lines, it's pretty easy to figure out the slope. So if you take a look at this first segment here, you can see that at least from 0 to 2, the slope, if I look at rise over run, or it's basically a slope of -2. We have to go down 2 and over 1. So we have a slope of -2. So if we graph that distance, or sorry, the velocity, it's just going to be a flat constant -2 between 0 and 2. And then you can see down here, the distance isn't changing at all, which means the velocity is 0. So we're going to jump up here, and between 2 and 4, the graph of the the graph of the velocity is just 0. Okay, so it's kind of a step function there. And now between 4 and 7, we've got a slope of, looks like we have to go up 3 and over 1. So we have a slope of 3. And so we're going to jump up here to a constant 3 between 3 and 7. Okay, I'll just connect them. Even though it's not a continuous function, I'll just connect them. And then finally we turn around here. Our distance now is decreasing, and so the slope is negative, so we're back down here, between 7 and 10. Right, and the slope is a -2, because you can see we have to go, from one point to another, we have to go down 2 and over 1. So that's what our velocity curve looks like. It's just a discontinuous step function here, just changing from these various velocities. All right, so if we look at the next one, we can do the same thing. And if you look at it, this slope, I'm going to write m instead of slopes. This is a slope of -2. Here's a slope of 0. Here the slope is, again 3. And here the slope is -2 again. So even though this graph for displacement looks different, it has the same graph for velocity. We're going to have a -2, and then it goes up to 0, and then it jogs up to a +3 until we get to 7, and then it goes down, back down to -2. Okay? So what's interesting to note is that even though we have different graphs for the displacement over time, the graphs for velocity are the same. Okay, and you can see it's basically just shifted up. The second, in part B, the second graph is just shifted up by 4 from the other one, which means basically we're starting at a different point, right? We're starting 4 units away from the origin, right here, instead of here we're starting at the origin. But other than that, the travel looks a lot the same. All right, so let's take a look at this one, the graph of velocity versus time. Okay, we're given the graph of velocity versus time. We want to find distance. So there's a couple different ways we could approach this. One, we could just look at the area under the curve, right? So I could just take a look at, okay, between 0 and 1, the area under the velocity curve gives us a distance. So that means the distance we've traveled, if we're going, say, 4 meters per second for 1 second, then in the first second we would travel 4 meters. So we can plot that point, right? So we have to make an assumption that we're starting at 0. We'll just assume that for now, okay? And then we could keep adding up these areas. So over the next 1 second, between 1 and 2, we go another 4. We're going to add that on to the distance we've already traveled, okay? And then here where it looks like our velocity went down to 1, so for the next 2 seconds we're just going to increase at that rate. And then, so you could see also another way you could do this is just, if you know the velocity, here we know the velocity between 0 and 1 is 4, so that means the slope of the distance graph between 0 and 2 is 4. So you can see I'm drawing a slope of 4. So you can do it with the area method, or you could also just look at slopes. And that works because we've got this step function here that for the velocity. If it were a curve, it's a lot more difficult to determine what the slope is at any point. So that's when we have to look at area. So, but we could just keep going. And okay, down here our slope is -2, or we could just keep adding area. But now remember, this area is negative. So this area between, say, 4 and 5, we're going to now we're going to subtract 2 over that next interval. And if we look at the next interval, we're going to go down another 2, oops, and then another 2. And let's connect that up. So these are all just every time interval we're just subtracting 2. Okay, and looks like we do that 5 times. So 1, 2, 3, and then 4, and then okay, looks like we're down to 0 at 9. And then our velocity goes up to +2. And the area here is 2, so our velocity, or our distance, is going to increase by 2 over the next time interval. So that's a graph of our displacement, or distance. I think I called it in this case. I'm assuming linear motion. So, so this is our distance over time. But this is not unique. And the reason for that is that we really don't know where we started here. We had to assume we were starting at 0, but we really don't know. I mean, if we had started at say 4, then all of these values would be increased by that amount. Now I'm going to run off my graph here, but you get the idea. Everything would be increased by 4. So I'd have a graph. Oops, trying to draw a graph that would look like that. So I would have a graph that would look like, let's see, I got to increase by 4. Let's see, 1, 2, 3, 4. Okay, so it's going to go through here. Every point just gets increased by 4. 1, 2, 3, 4. Okay. And so here I'd be at 4, and then I jog up. So that could also be another graph of displacement, given that we don't know where we started. Okay, all we know is the velocity, and that doesn't tell us anything about what our initial position was. And really, we don't. It's not just the initial position. We could also, at any point, would anchor this graph. If I knew where I was at t = 4, that would give me a point to anchor the graph, and then I could figure out the actual distance. Okay, so like if I knew that at t = 4, let's say that I knew we were at 6, then I could work backwards from that as well, and I could come up with a velocity graph. Now, obviously I don't have, it would look like, I don't have, my scale isn't going to fit it, but you know, it'd be the same shape, but anyway, you get the idea. It goes like that, sort of. If I knew that at t equals 4, we were at, say, 6 units away from the origin. Okay, so let's go on from here. Now, this is similar to what we did in 11.5. Here we go. Now in 11.5 we were given a graph, and we were asked to given the graph of velocity, say, and then we were asked to find points on the original function and graph the function. Now in this case we're given the derivative function, and we're given a point of reference. Right? We're told that the function value at 2 is 9, and we're given the derivative. So, and then we're asked to complete this table for the function itself, not the you know, we want the values for the function itself, and we're given an equation for the derivative. So what we're going to do to solve this is we're going to use the fundamental theorem of calculus. Fundamental theorem of calculus. Okay, now if you remember, so for example, if we want to find, okay, we're given f of 2, so I can actually fill in that value right here. And the fundamental theorem of calculus just tells me that if I take the difference between the function value at 4 and the function value at 2, that's equal to the integral from, whoops, not 0, from 2 to 4 of the f prime of t dt. Okay, and you did this again in 11.5. Now if we want f of 4, now since we know f of 2, then f of 4 is just equal to f of 2 plus that integral from 2 to 4. And f prime is the derivative, which is 0.82 to the t dt. Okay, now we haven't learned yet, we will, we'll get there, haven't learned how to actually evaluate this, but we can do it on our calculators. So I'm just gonna use my calculator to figure this out. Calculator. Okay, and I know f of 2 is 9, and when I evaluate that integral on my calculator, I got 1.11. And so when I add those together, I get 10.11. Okay, so the value of the function is 10.11 at t equals 4. Okay, and then we can just keep going from there. So I know that f at 6, there's a couple of different ways I could do it. I could integrate, I could, you know, just use, I could just continue using my value of the function at f equals 2, or t equals 2, and but I could also just use the previous values. So I know that f at 6 is equal to f at 4 plus the integral from 4 to 6 of f prime. But I guess I'm just gonna write the function, so 0.82 to the t dt. Okay, and that's just a matter of putting it in the calculator, and I'm going to use 10.1, and I'm going to add that integral that I get from my calculator, and when I do that I got 10.86. So fill in that value. Okay, and then we just keep going. The next one we want is f of 10. Okay, so I can just take my value at f of 6 and add the integral. I want to add the integral from 6 to 10 of 0.82 to the t dt. Okay, so When I do that, I get 11.70. Okay, and then the last one, f of 20, is just going to be f of 10. Now I could use f of 2 if I wanted to. Maybe I'll do that. I'll show you that. You could use any value that you know, okay, but it'll change what you need to integrate. So for example, if I wanted to just use f of 2, then I have to integrate because I have to add the whole area from 2 to 20 of 0.8 to t dt. Okay, so it doesn't matter. I just want to add on to some value I already know, and it could be the value at 10 or it could be the value at 2. But if I use 2 here, then I have to integrate from 2. So I add the whole area from 2 to 20. Okay, and when I did that, I got 12.29. So 12.29. Okay, so that's all we need to do. Now, one little side question is, can we find f of 0? F of 0. Oops. Oh gosh. All right. I can't write today. F of 0. Can we find f of 0? So we know, from the fundamental theorem of calculus that f of 2 minus f of 0 would be the integral from 0 to 2 of 0.82 to the t power dt, right? So if we want f of 0, we need to rearrange this so we get f of 0, because we know f of 2, right? We were given f of 2. So I can rewrite this as f of 0 is equal to f of 2 minus the integral from 0 to 2, 0.82 to the t dt. Okay, I'm just rearranging the equation. Basically, I could think of it as I'm subtracting the integral from both sides and then adding f of 0, so I get a positive f of 0. So if I plug in the values, I know that f of 2 is 9, and I know that, and I can evaluate this integral, and I got 1.65 when I evaluate the integral from 0 to 2, and so I get 7.35. Now the question didn't ask for that, but it's interesting to note. Just know that you can work backwards as well as forwards, right? Here we use the fundamental theorem of calculus to work forwards, but we can also use it to work backwards. All right, so now we are interested in figuring out the original function from the derivative, and we call that, the function that we come up with is called the antiderivative. So I feel like sometimes this notation is more confusing than it needs to be. It's not that difficult of a concept, but the way that they use a capital F and a small f, it's a little bit confusing. So let's just walk through this. If the derivative of f, so f, this is our original function, we'll call it original function, is f of x, okay, so capital F and f, so this is the derivative, so this is the rate of change, of the capital F function, right? Because it says the derivative of capital F is lowercase f, okay? So I guess I restated here that capital F prime is equal to lowercase f of x. Then we call capital F the antiderivative of f of lowercase f. Okay, so we're just asking what function has the derivative of f of x, this lowercase f of x. All right, so we're given a derivative and we want to find the original function. Okay, and that original function is called the antiderivative. All right. Let's just look at an example here, because now we're not actually in this chapter getting into figuring out equations for antiderivatives, but I mean, you just have to think about if I asked you what is the antiderivative of 2x, what this is asking is, what is the function, what function has a derivative of 2x? So what function has a derivative of 2x? Right? That's all that's asking. It's asking for the antiderivative, which means what's the original function that has a derivative of 2x? Okay, so you might be able to, you know, given that you've had some experience with derivatives, you might recognize that if I had x squared and I took the derivative of that, that's 2x. So x squared, so x squared is an antiderivative of 2x. Okay, we're just going backwards. We're underiving. Okay, we're undifferentiating a function. Okay, we're given the derivative and we want to know the original function. Now the other question you might think is that the only antiderivative of 2x? And the answer is no, because if you take the derivative, let's say of say x squared plus 8, now the derivative of constant is 0, so that's also 2x. Or if you had the derivative of let's say x squared minus 6, that's also 2x. And you could come up with an infinite number of other equations that would have that same derivative. Now you might notice it's just the constant that's changing. So hold that in mind. We're gonna get to that tomorrow. Today we're just going to look mostly at antiderivatives from a conceptual and graphical point of view. All right, so if we're given information about a function and we want to graph the antiderivative, we just need to keep in mind that okay, so this capital F is an antiderivative of lowercase f. So what does that mean? That means that f prime is equal to f. So this is our derivative. And this is the original function. That's not very mathematically rigorous notation, but I want to make this, I'm hoping to make this make sense to you. All right, so the derivative of capital F is lowercase f. So what that's telling us is that f, because it's the derivative, it gives us the slope. It gives us the instantaneous rate of change of the capital F function. So I'm just going to write f gives the slope. Slope gives the slope of capital F at any point. Okay, so if we think of it that way, these statements will make more sense. So if lowercase f is greater than 0, then that means the slope of the original function is positive, which means that capital F, which is the original function, is increasing on that interval. All right, and if lowercase f, okay, the derivative, slope, if the slope is negative, right, so you just interpret it as a slope because it's the derivative of capital F. So if the slope is negative on any interval, that means it's decreasing. Okay, and then again, if the slope is 0, then the original function is just constant, right? Right, it's just flat. All right. So let's take a look here at an example. Okay, let's take a look at this example. We're given the graph of a derivative. All right, so this is the graph of the derivative, and they give us the areas for certain portions of the graph. And what do we want to do here? We're told that f of 0 is 10. That helps. And we want to sketch a graph of f of x, the original function, okay, and give the coordinates of the local minima and maxima. All right, well, what I'm going to do is just first of all create a table. Before I make my sketch, I'm just going to make a table of values. I want values for x and I want values for f of x. And I'm going to base that off of this graph, okay, because we're given areas. So that helps us, you know, because the integral is going to give us help us get the original function. Now we're first of all told that at 0 the function value is 10, okay, and then this area between 1 and 2 is 14, right? So we can easily find the function value at 2 by taking 10 and adding the integral from 0 to 2. So I'm just again using the fundamental theorem of calculus. Okay, so we're going to take 10 and add the area 14. And so we get a value of 24. Okay, so now I can plot these points. Now I'm going to wait because I want to scroll down to have room to write a little better. But this is just giving us values that we can plot. Okay, so let's see. At the next area we're given is we're told that this area is 20, but it's below the graph. So we're really going to treat this as if it's minus 20. Okay, so right, because the integral is going to be a negative, and so if we want to find the function value, now I know the integral between 2 and 5 is minus 20, so I can find the value at 5. It's just going to be the value at 2, which is 24, plus the integral from 2 to 5 of f prime of x dx. All right, so if I take 24 and subtract 20, now I'm at 4. Okay, so my function value at that point is 4. And you can see here this graph is below the x-axis. So f prime is negative, right? The derivative is negative. The slope is negative of the original function, and so it's decreasing during that during this interval between 2 and 5. All right. And then finally, we can also find a value at 6, right? So we can take the value at 5 and add the area between 5 and 6. So we're adding the integral from 5 to 6 of f prime of x dx. Okay, and then we're told that that area is 12, so we're just going to add 12 to 4 and we'll get 16. So now we have a table of values, and we can just plot those values. We can also look at the shape of the graph. Based on the shape of the derivative. So I'm going to draw an axis here. I'm going to try to draw it, straight above, or straight below the other one, so I can sort of. So let's say that's 6, and try to eyeball this 5, 4, 3, 2, and 1. I just want to draw it straight below. So let me fix that. That should be a 1. All right. All right. Well, we can plot the points we just found. So let's do 5, 10, 15, 20, and let's say this is 25. 10 and 5. Okay, so we're told that at x equals 0, the value of the function is 10. Okay, so this is, I should probably label these axes too. So I'm graphing f of x, right? I had the graph of f prime of x, and I want to graph f of x. Okay, and now, okay, so at 2, the function value is 24, which is about there. And then at 5, we're at 4, so I'm going to say it's about there. And then at 6, we're at 16, so I'm going to say it's about there. Okay, and then if we connect those dots, we can we'll graph what the function is. Now it's also interesting to look at, you know, how is this area increasing? If I were to break this up into, you know, even chunks, you can see that it increases quicker at first, and then it kind of slows down. And then essentially here, what's happening? Where our f prime is 0, right? So our slope right here is flat. So when I graph this, I'm going to kind of reflect that. It's increasing quicker at first, and then it slows down, right? And then during from 2 to 5, the function is decreasing, right? Because the rate of change is negative, right? And so so it's going to look something like, let me see if I can make this look decent. Like that, right? And again, if I slice it up, I can tell it's increasing the quickest during, you know, this interval, and much quicker than it's increasing at that interval. So I'm going to kind of reflect that here. You know, slopes are going to become less negative until we get to here, which is where the slope is 0. And then we're going to start increasing again, because our graph of f prime is above the x-axis, right? So we're going to come up like this. So this is sort of what the original function would look like. Now I can label some of these points. This is 0, 10, right? This point right here is 2, 24. This point down here is what? It's 5, 4. And this point here is 6, 16. Okay. And we're asked to find the local minima and maxima. So I can say that, you know, based on this graph now, that we have a local maximum at 2, 24, right? And you can see the critical points would be at 2 and 5, right? So, and obviously it looks like the point at 2 is a maximum. And we also have a local minimum at the point 5, 4. All right. All right. So you can see we also, you know, just by looking at how the area is increasing, we also determine something about the concavity of this graph, right? You know, here for this graph, we said it was increasing quicker. Well, maybe I should use my mouse because I think it registers better, at least the pointer registers. So in this first part of the graph, we're increasing quicker, and then we're slow down until we hit 0 and then turn around. So we can also make some statements about the concavity of an antiderivative based on the derivative of a function. Because the derivative of the derivative is the second derivative. So if f, lowercase f, is the first derivative, then the derivative of f is the second derivative of the original function. Okay, so if capital F is the antiderivative of f, meaning that f prime is equal to f, so f gives the slope of capital F, of capital F, oh goodness, oh come on, can't get that in, okay, of capital F, right? And f, the second derivative, right, f double prime, is the derivative of lowercase f. So f prime gives the concavity of f. Okay. So now we can look at the first derivative of the derivative, which is the second derivative, in order to determine some information about the concavity of the antiderivative. All right. So if f prime is greater than 0 on an interval, then f is increasing. Okay. So lowercase f is increasing, which is the derivative, right, is increasing. And the graph of uppercase f, which is the antiderivative, is concave up. Concave up on that interval. Okay, because essentially lowercase f prime is the second derivative of the antiderivative. Okay, all right. So so now we're looking at the derivative again of the function, which is the derivative. So it's the derivative of the derivative, and if lowercase f prime is less than 0 on an interval, then f is decreasing. Okay, so it's less than 0, so decreasing, negative. Decreasing. And so that's also telling us about the concavity of the antiderivative, which is capital F. And so capital F is concave down. Okay. So anytime it's 0, too, that tells us where an inflection point is. So, or potential inflection point, right? So inflection points of the antiderivative occur when lowercase f, which is the derivative, and changes from increasing to decreasing. Okay, so we can look at where it's 0, right? We can look at where so hard to this notation is so weird, but the lowercase f, if we look at the derivative of the lowercase f, we can when that's 0, that's where we would have potential inflection points, because the derivative of lowercase f is the second derivative of the antiderivative. So all right, so I have some practice problems here. I think there's just 2. They're very similar to what's on the homework and some of the problems we just did. And so I want you to try those. The answers will be on Canvas. The only thing different is that I ask here where the inflection points are. Okay. So you might take a look at, think about how you would find the inflection points. Now, you're not going to be able to find the exact inflection points because you're not given enough information, but think about where the inflection points would be given this graph of, this is the f prime, capital F prime. All right, so we'll talk to you later.